to introduce Stan here in this symposium. Thank you very much, Stan, for joining us. So Stanley, he is the Nobel laureate for last year. Brought a lot of honor to our field, well-deserved. Many years of excellent science, systematic work on intercalation compounds, in fact, on all kinds of energy materials. And so, Stan, we're all looking forward to hear you. Thank you for joining us.
Thank you, Doron. I hope you can hear me okay.
Yes, yes, yes. The system so far so good. It works well.
Good. So I want to talk a little bit about the origins of the lithium battery and some of the future challenges. And clearly, in the last talk, we had some of the big challenges of layered oxides. But I'm talking to you from upstate New York and bright sunny morning. So it's nice here. I should emphasize that almost all the work I'm going to talk about is supported by the Department of Energy. So I want to thank ESSO, which is now ExxonMobil, who had the willingness to take the risk almost 50 years ago in 1972 to invest in lithium batteries. And I show you, we just heard about single crystals. These are the typical single crystals we used in the batteries at Exxon. So we're going, as it were, full cycle. And two of the devices that Exxon built, this was a marketing giveaway they gave to potential customers. And this particular one is still in my office and still working. So very well made batteries, more than 40 years old, still operate. And Glenn Amatucci and his colleagues at Rutgers, in fact, looked at some of these cells here a few years ago and showed that they still had 70% of their original capacity after 40 years. Some larger cells Exxon built were for the EV show in 1977. And these are about 6 inches by 4 inches by about an inch thick. So they made fairly large batteries in those days, and they are mostly for electric vehicle applications. So these particular cells, last October, after the prize was announced, Bob Hamden and I looked in our basements and we were able to find some of these original cells and one of the original Exxon brochures. So these are now in the Nobel Museum in Stockholm if anybody wants to see them. So let me get back to what was special about titanium disulfide and why it was so interesting at the time. And I would just like to point out at this stage is that Jeff Dahn got his PhD working on titanium disulfide. So back in those days, it was the hot material. So if you look at titanium disulfide, it's what I would call a metallic conductor. So you don't need to put any carbon black in it. And this gives it the advantage that the reaction occurs on all the surfaces of the titanium disulfide, not just where the carbon black, the titanium disulfide, and the electrolyte meet. So inherently, it's got a higher rate. And being a metallic conductor, the electrostatic repulsions from the lithium ions are minimized. So you can see a typical discharge curve here. This is at 10 milliamps per square centimeter discharge and charge. And I went back and looked at in the original patent, and the loadings of TiS2 we used back in those days varied between 20 milligrams per square centimeter up to over 100. So we're using very high loadings. Jeff has already mentioned these are layered structures, and there's a tendency for the transition metals to go into the lithium layers. This has some good and bad consequences. Obviously reduces the diffusion of the lithium, But in the case of titanium disulfide, we intentionally, in the commercial product, put about a 0.5 to 1% titanium in this layer. This, in fact, reduced the corrosion of the material substantially. Now, I list at the bottom all my colleagues that made this possible. So I said TiS2 was good for lithium. Linda Nazar, who's speaking a little later, showed that TiS2 is also very good for magnesium. And this, in fact, the plot I show of hers here is for the spinel phase. So TiS2 exists in 2 different phases. And you can see very little polarization, very good cycling retention. But this is at 60 degrees centigrade and the lithium is at 21. The real challenge for all these magnesium batteries is the slow diffusion of the magnesium. And at the moment, no one has been able to get a second electron into a cathode using magnesium. So that challenge has still to be addressed. The really big issue with magnesium, you can see the voltage at half discharge is about 1.2, 1.3, compared with about 2 to 2.1 for lithium. So magnesium suffers from about a 1 volt deficit, which I think is not going to really allow it to be used in commercial systems. Calcium will be more promising, and being a larger cation, it might diffuse better. These materials are again being studied. In this case, it's vanadium disulfide, again a metallic conductor. And 2 groups have looked at this for sulfur batteries. Being a metallic conductor, it can be the conductive substrate for sulfur. And I'm not going to go into the details of these cells. You can look at yourself. And you can see with this, you're getting about 800 milliamp hours per gram with a liquid electrolyte. And Linda has shown that with a solid electrolyte, you can also cycle this material with very good coulombic efficiency and capacity retention. So these layered sulfides are outstanding cathode materials, with one exception: their voltage is too low. Their big advantage is the metallic conductivity. So I don't think I need to go through this slide with this audience. This is just a little bit of history. All the batteries we use today with lithium are intercalation based. In the first steps, beginning in 72, we used lithium metal anode. Then Akira Yoshino went across and started using carbonaceous materials. I should say Exxon, in fact, switched to lithium aluminum in their commercial cells. Akira went to carbon. Carbon takes up half the volume of the cell, and you need 72 grams of carbon to store 7 grams of lithium. So if you want to increase the energy density, you have to get rid of the carbon eventually. A lot of work on tin or silicon. There's challenges there. Tin will cycle at 99.95 coulombic efficiency. Silicon isn't close to that at the moment. And the real push is now it's gone full circle, and people are now working on lithium again. On the cathode side, we started with the lead TiS2. Then John, who was working on the magnetic behavior of cobalt oxide, recognized it had essentially the same structure, switched to cobalt, and showed that it cycled very well. And this is still the commercial material used in things like cell phones and laptops. Because of the cost of the cobalt, most people have now switched to NMC, NCA, and you heard all about that from Jeff Dunn, who's one of the primary inventors of the NMC materials. Then John came up with the lithium iron phosphate materials. They were very actively used for many years for utilities in the US. They've gone out of favor now relative to NMCs because of the lower energy density. And I'll finish this talk with some discussion on the vanadium phosphates. These have the advantage if you can put 2 lithiums in there, 2 electrons, or a magnesium or a calcium, you can get over some of the penalties of working with the heavy phosphate materials. So let's just look at where lithium batteries are used today. We're now in Stockholm. 2 of the physicist Nobel laureates and I had a live conversation with the astronauts on the space shuttle, and they were in the middle of replacing all the nickel metal hydride batteries. We stored the energy from the outside solar cells with lithium ion batteries. To them, the big advantage is that lithium ion batteries were half the size and would last twice as long. So they were very excited about it, and I think they completed this change in January of this year. I think most of you know all the different areas where lithium batteries are being used. They're clearly very important for enabling renewable energy. They are being used in all sorts of vehicles, and I take 2 extremes here. This was a small 2-seater that my wife and I rented in Bermuda last year. And as we found out, range anxiety is real. We were told that if we drove to the far end of the island, we would have to recharge before we could get back, and that there was a recharging station there. Well, we got to the far end of the island, the recharging station was still being built. But we found one part way back, and we managed to charge enough to get back. At the other stream of electric vehicles are 2 trucks. This is at the test track of Peterbilt in just north of Seattle. And you can see the large lithium-ion batteries in the back here. And I took both these trucks around their test track. And this particular truck is now in the Los Angeles docks, moving containers from the ships to the local distribution centers. And to the right is a garbage truck, really an ideal use for electric vehicles, because it stop-start a lot of lifting and lowering down. And at the bottom here, you can see 2 vehicles that the UK ambassador shipped to Stockholm for the prize ceremony. This one is an electric Jaguar, and on the right is a London taxi built jointly with Volvo. And she used this to go to the receptions. I get lots of questions from people. Well, you got the Nobel Prize, so nothing needs doing with lithium iron anymore. And I say, that's not the case. And as Jeff showed, we have many limitations. The real issue is today's lithium-ion batteries store much less than 30% of their theoretical volume capacity and of their weight. And you can see just some numbers in the red circle here. Lithium iron phosphate is between 11 and 14%, and the layered oxide can get as high as 25%. So there's a huge opportunity to increase the stored energy density, and I'm part of the Battery 500 consortium, and our goal is to get these numbers here in this column, up to 500, and I'll show you data in a few minutes. To do this, we've essentially got to eliminate most of the graphitic carbon. We've got to make an alternative work. We've got to use more of the lithium in the cathode materials. As Jeff has shown, this is going to be really challenging for the layered oxides. And this opens up the opportunity for the phosphates, which are safer and more stable. The other issue we need to address if we want to increase the energy density is to get rid of more of the dead weight. We can do this first by just making thicker electrodes, so we can cut down the amount of current collector and separator. So if we double the thickness, we can cut out half the current collectors and separators. So let me look at the layered oxides, and I'll build a little bit and not duplicate too much of what Jeff has said. For electronics, lithium cobalt oxide still dominates. For the other materials, the mixed metal and MCAs now dominate. There's a major effort to get rid of cobalt, and as Jeff showed, it's not really necessary. This is driven commercially, mostly by a cost. So going from 333 to 622 cut the cost of the cathode material by 40%. And then obviously you've solved some of the environmental and child labor issues. So this is a classical plot now from Sun's group in South Korea. I think everybody knows this. The less nickel you have, the more stable the material. The more nickel you have, the less stable, but the more nickel you have, the higher the capacity. And also the capacity retention is worse with the high nickel, just because you're going to tend to go to a higher voltage. So this is one of the challenges. Jeff has already mentioned that aluminum, magnesium help, but they reduce the capacity. The real interesting challenge for everybody in this field is how high can you increase the manganese content and still have decent structural stability and capacity retention. So I just want to show you the status of the Battery 500 project. For the first 2 years, we used 622 as our standard, and everybody in the project used the same material from the same supplier. This material has very good electrochemistry, and our goal a year ago was to meet 350 watt-hours per kilogram, and you can see we attained this fairly easily over 250 cycles, and now it's many more cycles. The capacity is retained very well. And I should say there's no fudging the data here. After the cycling was accomplished, the cell was actually weighed, the volume measured, so we know exactly what the energy density was. And the volumetric energy density of this cell was just over 700 watt-hours per liter. And these data were collected by my colleague Jay Xiao at Pacific Northwest National Lab in conjunction with Idaho National Lab. So to get higher than 350, we needed to increase the nickel content. So we wanted to see whether 811 was potentially as good as 622. I don't want to go into all the details on this slide, but just look at the drop-off here as you increase the current density as much more than the drop-off with 811. So 811 is a more high-power material. Increasing the loading of the 811 from 5 to 25 milliamps per square centimeter is not as damaging to the rate capability as it is to the 622. So the Battery 500 consortium has switched over to 811. Okay, so this data is actually to 4.6 volts. We know that 4.6 volts gives bad capacity retention, so most of our data on long-term cycling is cut off at 4.3 or 4.4 volts. Let's just look at really what the issue is with these layered oxides. As Jeff discussed, 210 seems to be a magic number for long-term stability, but what we can do with this material is use all of the material at high lithium contents. So you'll see here, this material, and in fact, all the layered oxides have this first cycle loss, and this material, 811, is about 30 milliampere hours per gram, and this is cycled up to 4.4 volts, and this is using typical meatball type materials. If we could eliminate this, we could increase the energy density without stressing the material by going to very low lithium contents. So let's look at what's important for this first cycle loss. I show you here 4 things that are not important. The first cycle loss is independent of the loading of the active material. It is independent of the nickel content, so whether it's 40%, 60%, 80% doesn't make much difference. It's independent of the sort of carbon we used as the conductive material, and it's really independent of how much carbon and binder we use. So these are not important parameters. What is important is calendering, so we need better contact between the particles. So here in black is the effect of no calendering. If you see some calendering reduce this first cycle loss. We also found that if we do after doing a constant current discharge, we now go to a constant voltage discharge, that we gain some of this capacity back. And if we do calendering and constant voltage discharge, we get even more back. So this is suggesting that slow kinetics is the problem at high lithium contents. And I should emphasize Ping Lu at San Diego has studied the impact of taking different amounts of lithium out, and it makes essentially no difference whether you take out 80%, 70%, or 50%, you get exactly the same first cycle loss. So it's the last 10% of the lithium, so above, say, 85% lithium content, that controls everything. So we measure the diffusion coefficient. The black is the indiffusion, and you can see above about 80% lithium, we're seeing a 2 to 3 orders of magnitude drop in the lithium diffusion coefficient. And Anton van der Ven relates that to the diffusion mechanism, which he says is a divergency mechanism. So what you need is 2 vacancies for one lithium to jump through a tetrahedral site to the neighboring octahedral site, and the number of these drops off dramatically as the lithium content increases. You'll see that this is not really an issue on charging, except maybe the last 5 or 10%. So these materials are very fast chargers, but not so fast discharges. So this is again saying diffusion is limiting it. On the right-hand side here, I'm showing you the effect of charging to different voltages. And you can see, obviously, the higher the voltage we go, the more capacity we get. But as we go to extremely high voltages, we're getting a number of side reactions and obviously damaging the surface of the material, if not the bulk. We're getting much more polarization. If we increase the temperature from about 21 to 45 degrees centigrade at 4.4 volts, you can see we've eliminated almost all the first cycle loss. It's again indicating that this is a diffusion controlled reaction. If we go to 4.6 volts, you can see that we're now getting some increased polarization, so we're getting some damage to the material, more resistance on the surface, and this is preventing us from getting such a reduction in the first cycle loss. And if you go to 4.8 volts, it's even more damaging. So clearly the message here is we shouldn't go above 4.4 volts, and diffusion is again controlling the situation. So we wondered whether lattice modification might help. We knew in the olivine lithium iron phosphate that substitution helped those materials increase the rate and gave us a larger capacity. So we looked at substituting with a lithium niobium oxide, and we basically coated the meatballs with lithium niobium oxide solution, then fired the material at 400 degrees centigrade, and we got a coating on the surface which diffused a few nanometers into the surface, so we had partial substitution. And I think you can see this at the 1% level did no damage to the total capacity on charging, and it reduced the first cycle loss by about 40%. And this is at room temperature. If we go to higher temperature, this is further reduced. So we believe by appropriate substitution, this first cycle loss can be reduced. We know with aluminum it's reduced a little bit, but not by as much as using niobium. So we believe you need to do substitution and coating. The interesting question here is, why does lithium cobalt oxide not show a first cycle loss? And I show you some data here comparing 811 with lithium cobalt oxide. In black here is the room temperature data, 811, and you can see the large first cycle loss. Here's the data for at 45 degrees centigrade, where it's almost all gone. If we then do a constant forces discharge, we get it essentially all back. And this is just an enlargement of this part up here. Okay, so this has been held for 100 hours here. If we do this for lithium cobalt oxide, to charging to exactly the same amount of lithium, you can now see there's essentially no first cycle loss, and it makes no difference really where room temperature or 45 degrees centigrade. So we believe by the appropriate modification of the NMC, we should be able to eliminate most of this first cycle loss. We haven't found the solution yet, but we believe it's out there. Let me just show some opportunities for future study. I've talked about TiS2. I skipped over moly disulfide, which is what Moly Energy used in the 80s as a commercial cells. I've gone over cobalt oxide. I'm not going to discuss the lithium iron phosphate except to show you the structure here, and that in many cases there is no first cycle loss in lithium iron phosphate, despite it being a one-dimensional diffuser. And I'll talk in a minute about lithium vanadium phosphate. So in lithium iron phosphate, it's coming back in favor. I think Tesla announced that the Chinese cars will use lithium iron phosphate because they can get a much longer range. It's lower cost, and they're saying it will go 1 million miles. But it has a lower energy density. We can switch to manganese phosphate and get a little bit of that energy density back. But the real issue for us was, is a 2-electron redox system possible? And in particular, can a crystalline lattice withstand 2 lithium ions going in and out of the structure? So we've looked at that, and I won't talk about high manganese contents materials. There's a lot of interest there. I understand BASF is actively working on it, and the disordered rock salt is under study. There's a very large voltage change between fully charged and fully discharged. So let's look at this vanadium phosphate material. This is a 3-dimensional structure with tunnels in all 3 directions. Alan Jacobson at Exxon was the first person to work on this, and he was interested in oxidation catalysts. And after a lot of study, we were able to make good material of this phase by a solvothermal process where we reacted vanadium trichloride and phosphorus pentoxide in 95% ethanol. You have to have a little bit of water there, or the ethanol will reduce the vanadium trichloride too much. It just needs about 3 days reaction. I believe it's possible to do it in less. And after that, you form this vanadium phosphate phase with hydrogen in the channels. A mild heat treatment removes all the hydrogen, and then you have your empty crystalline lattice. This is the structure of the material. Little single crystal cuboids. These are 100 to 200 nanometers in size. Using other synthetic techniques, we can make much larger crystals, but they had a very poor cycling behavior, and if you used high energy ball milling to make them smaller, then you damage the structure, including, in fact, changing the lithium sites that were occupied. So you can see, using this material, we get 2 plateaus, vanadium 5 to vanadium 4 just under 4 volts, then vanadium 4 to vanadium 3 at about just over 2 volts here. So then you see there's some ordering transitions in here, which apparently have no effect on the cycling ability. And in fact, in this range, this material has the same capacity at 1 C rate as at C over 50 rate. So very, very high power capacity there, but that's not the case at the high voltage. You'll see the black here is the first cycle, the purple is the 50th cycle, and you can see there's essentially no change whatsoever in the behavior here. So there's no capacity loss. This is really proof of concept that a crystalline lattice can tolerate 2 lithiums going in and out without damaging the lattice. We have shown using a related vanadium phosphate structure, we can also cycle 2 sodiums in and out of the lattice. We cannot cycle magnesium in this lattice because the magnesium, in fact, on the first discharge, abstracts oxygen forming magnesium oxide. So let me conclude with a few comments. It's my belief that lithium intercalation systems will dominate for the next 5 to 10 years. NMCA will be the dominant phase for grid and vehicles. It will go to close to 0 cobalt, if not to 0 cobalt. The phosphate systems will have key markets, and these are probably growing, particularly with now Tesla promoting it for their long-range vehicles. The real limitation, besides the graphitic carbon anode, is that we need a safe and stable electrolyte. At the moment, the present carbonated electrolytes have a number of additives in them to stabilize them, but even so, they're still not stable. They react too much, there's still some dissolution. So we need more research on the electrolyte. And I think the question is still out, can solid state give the required power densities at reasonable temperatures? Now, in vehicles, you don't really want to go much above 30 or 40 degrees. I think grid storage, you can in fact use 60 or 70 without too much problem. If we had stable electrolytes, we could potentially go to higher charging voltages and use lithium metal. The real driving force, my belief, for the next 5 years is that energy storage can help to mitigate climate change. We can have greener vehicles. We can enable renewable energy. We can eliminate dirty peaker power plants. Here in Binghamton, about 8 years ago, an 8 megawatt hour lithium ion battery was built next to a coal peaker power plant. After 1 month of operation of the battery, the power plant was turned off and it's never been turned on again. So they have a valuable use in addition to helping renewable energy and cars. And this will enable us to leave a greener world for our children and grandchildren. And I'd like to thank you all for listening, and I'm willing to answer any questions.
Thank you very much, Stan, for this highly educative talk with a lot of messages. Well, we have some time for discussion, and there are several questions that were accumulated. I can read maybe some of the questions. I see here a question from Alex Schechter from Ariel University in Israel, and he asked, do you think that lithium-ion battery is a viable solution for large-scale energy storage? To what extent we can use lithium-ion batteries for this purpose?
I think solar is a beautiful application because clearly in your own home, batteries are the perfect storage opportunity. For large scale, right now, just outside San Diego, they just opened up a 250 megawatt hour battery. I don't think it's being used for solar, but it obviously could be. In the Los Angeles area, they've got approval for building a 1 gigawatt hour lithium battery storage system. So I think that will totally be applicable to solar photovoltaics. So I think the answer there is yes, it can be used. It all depends on the, I think, the economic viability of each project.
Well, I see here a question, which is interesting, about the lithium vanadium phosphate. And there is a question about the usefulness of the low voltage plateau around 2 volts. So to what extent the fact that we have 2 plateaus may limit us in use for high energy density applications.
This is a concern we had at the beginning. All our electrical engineering friends said, stop worrying about that. It only matters if you're using 1 or 2 cells in a battery. If you're using a lot of cells, then you're using DC to DC conversion to get up to, say, 300 volts or 600 volts, and they can handle it. It's going to cost a little bit more, but it's not a real issue. Clearly, it'd be nice if there wasn't such a big step. And we've been trying to look at ways of, in fact, maybe dropping the 4 volt down to 3.5 volt and increasing the other one to a slightly higher voltage. But I think what we tried to do there was just show proof of principle that no, you could use intercalation reactions to transfer 2 electrons. And if that's the case, then we just need to look for better hosts that maybe have not so much of a change. But it's feasible to do 2 electron reactions right now. I'm not suggesting that vanadium phosphate is going to be the next commercial battery cathode, but it shows promise and that maybe there's some better materials out there.
Now, there is a question about the phosphates that you need a nanostructure, and there is an issue of volumetric specific capacity and the amount of carbon or conductive agents that you may have to add. So in the case of this lithium vanadium phosphate, what is the situation with the transport properties of this material?
With the lithium vanadium phosphate, I say I didn't show you the data, but in the low voltage regime, it's extremely fast charging and discharging. C rate is the same as C over 50. But in the high voltage region, it's a true 2-phase reaction at the moment. So the rate capability is much lower. In the lower voltage regime, it is a 1-phase reaction, even though there's some transient ordering of the lithium. So we have to solve the high rate capability at the high voltage. We basically got to turn that into a 1-phase behavior, just like we showed for the olivine lithium iron phosphate, which is a 2-phase reaction when you use large particles. If you use more nano-sized, it goes to 1-phase. But you can also dope it with a few percent of magnesium, or as we used in those days, a few percent, 5% of vanadium, and you convert it to a 1-phase, and then you get much better rate capability. And I think the amazing thing about lithium iron phosphate is probably the highest rate cathode on the market at the moment. It's extremely fast, despite being an electronic insulator. So I think those are challenges we have, but I think we can solve them. And we don't use much carbon. It's about, I think, 5 to 8% in the vanadium phosphate. That's higher than used in NMC commercial, which is about 2%.
Good. So I believe that we have to move further. Stan, again, thank you very much for spending time with us, sharing your long-term experience. And hopefully we'll see each other soon face-to-face without masks, not just by the electronic media.